Hello everyone, and welcome back to another Big Ideas lesson. Today we are starting off Unit 7. Now, Unit 7 is a little bit different than all the other units. We're basically going to be doing what we always have been doing in algebra, dealing with variables, dealing with exponents, but to a new degree. We're going to be having a bunch of variables and exponents in a line, or in an equation, or in an expression, and having to figure out how to best simplify or break it up. To start off with, let's talk some definitions, because on page 206, which is where we're starting today, there are quite a few of them. Let's start at the very beginning. The first term is called a monomial. And if you know what mono means, this one might make a little more sense to you. Mono means one, and nomial means term. It's one term. Now, we've talked about terms before, just not in great detail. The key is, a term is just a way of saying any grouping of numbers and variables being multiplied or divided together, but it's only if they're being multiplied or divided. So for instance, 5 is a monomial because it's just one term. It's just one thing. X is also a term. It's just one thing all on its own. We get a little strange when we have more things introduced. 3y is just 3 times y. This is still considered one term because everything is being multiplied together, 3 times y. Let's keep going. What if I had something like negative 2z squared? Now, this one might confuse a couple people. Is everything in here being multiplied or divided? The answer is yes. Negative 2z is the same as negative 2 times z. And since it's z squared, that means there are two z's multiplying each other. So everything is being multiplied. Exponents count. We could take this one step further and have a term with just a bunch of exponents, like x to the 7th y cubed. You can even have something being divided. For instance, if I had 2 divided by, let's say 2z divided by 5. All of these are monomials. All of these are terms. So, if monomials are just one term, where everything is being multiplied or divided, that means we also have another definition figured out. Down below, a couple spaces down, we have something called a binomial. If a monomial is one term, what do you think a binomial is? It's two terms. Two terms. Now, a binomial is where you have two terms being added or subtracted together. So, for instance, we know that 5 is a term, we know that x is a term, 5 plus x would be a term, or 5 minus x would be a binomial. Both of these are binomials because we have a term here and a term here. There's two of them per expression. Of course, you can get wacky with these as well, like 2z cubed minus 7x. That could be a binomial. You can even have something like x squared plus x. Now, keep in mind, the reason why we call all of these binomials is because they can't be simplified. If I wrote down 2 plus 3, that's not a binomial because this simplifies to just 5. That's one term. None of these can actually simplify any further. You might be saying, Mr. Strager, what about this one, this x squared plus x? We learned all the way in Unit 1 that, unfortunately, variables don't like combining with things that don't look exactly like them. It's a little problematic. They don't combine with anything that doesn't look exactly like them. Keep in mind that x squared is x times x. So x squared plus x is x times x plus x. If it was times another x, it would have just been written out as x cubed. But it's not, it's plus. Or if this was a plus sign instead, with this first one, it would be x plus x plus x, and that'd be 3x. Those could be simplified. Multiplying and adding don't simplify each other. So we would say that x squared plus x is as simple as it gets. There is one more I want to talk about, and this is going to be the most important one for this unit, a trinomial, which you may have guessed has 3 terms. So we can keep on going with this pattern. For having 3 terms, I could have, I don't know, a 7, and then something that won't combine with a 7, like an x, and then something that won't combine with an x, like maybe an x to the 5th. Sure, that's a trinomial. Or something like 2x squared minus 3x plus 2. That's a trinomial. Or even a plus b plus c. All of these are trinomials because there are 3 terms being connected by addition or subtraction signs. Now, we're going to talk about something a little bit different. You see how with our monomials, we have monomials where some look very simple and others look very complicated. For instance, 5 is very simple. We know exactly how much 5 is. X, we don't know how big it is. It might be 1, it might be 2, it might be 20, it might be 20 million. But we do know that a single x is much smaller than x to the 7th, right? So this one's probably going to be much bigger than this. We actually have a way of quantifying this. We have a way of quantifying the strength or the power of a monomial. It is called the degree. Now, what I'm going to do is I'm going to give you the exact book definition of the degree of a monomial, but I don't like this definition, so we're going to be able to mess around with it a little bit. The degree of a monomial is the sum of the exponents of the variables in the monomial. The sum of the exponents of the variables in the monomial. It's a little bit of a mathy definition, but maybe when we get some practice in, we'll be able to see why this is relevant. I don't like this definition, however. I like to think of it in a different way. The degree of a monomial is what happens when you add together every single variable being multiplied in the monomial. Just count up the number of variables being multiplied or divided, and you've got it. You've got the degree. So let's start off with this. How many variables, just variables, are in this expression? Well, 5 isn't a variable. It's a number. You would say this has degree 0 because it's just a number. Okay, what if instead of 5, I had 5x? Now how many variables are in this problem? Well, 5 is a number, and x is being multiplied. This would be degree 1, since there's just one x being multiplied in our problem. For those of you who want to follow the definition in the textbook, you may notice that x is the same as x to the first power. So we would add up all the exponents, and we would say, oh, there's 1. Let's make one that's a little bit trickier, though. Let's say I had 5x to the 5th. Aha, now how many variables are being multiplied in this problem? You might be tempted to say 1 since you only see one x, but remember, x to the 5th is the same as x times x times x times x times x. This would be the same as 5 times x times x times x times x times x. So, how many total x's are being multiplied in this problem? There are 5 of them, so it would be degree 5. Again, for this following definition, you can just count up the exponents in the problem. X to the 5th, so the answer is degree 5. All right, what if I gave you one like this? Now we're getting a little more complicated. Now we got more variables in here. Well, if we count up all the variables in the problem, we know that x to the 7 means there are 7 x's. Y squared means there are 2 y's. So 7 x's and 2 y's, that means there are 9 total variables. It is degree 9. Last one. What if I gave you 3 to the 10th power x cubed y squared z? Now be very, very careful here. You might be tempted to say, oh, 10 plus 3 plus 2. But remember, we're counting up the exponents on the variables. 3 to the 10th power is just a number. It's a big number. It's 59,049 big, but it's still just a number. X cubed is just a number. Or sorry, x cubed has 3 x's. Y squared has 2 y's. And z is the same as z to the 1st. There are only 6 total variables. So this is degree 6. All right? So those are degrees of a monomial. Now, monomials, binomials, trinomials, quadrinomials, pentanomials, hexanomials, you can go on and on with these names. You can keep going up in the number of terms you have, but it seems like a bit of a hassle to have to remember every single name. Like, I'll tell you this much. I know that 9 is nonomial. I know 10 is decomial. Even I don't remember what an 11 nomial is. Or a 15. Or a 320 polynomial. I don't know. So we have a general term to describe any of these nomials. It's called a polynomial. And polynomial means many terms. When we have many terms, it's a very inclusive term. A trinomial has many terms, according to the definition. A binomial has many terms. We even include, oddly enough, a monomial in this definition. A polynomial is either a monomial or sum of monomials. In other words, it's either just one term or a bunch of terms being added together. Polynomial is the general word for all of these. A monomial is a type of polynomial. A binomial is a type of polynomial. A trinomial is a type of polynomial. When we start looking at polynomials, they can go very long, but I'm going to give you an example here that's just 4 terms long. You could call it a quadrinomial, but we're not going to. We're just going to call it a polynomial. Let's do this. This would be an example of a polynomial. We have many terms here. There's 1, 2, 3, 4. Now, we do have a way of quantifying the size of a polynomial as well, and we call it the degree of a polynomial. Here's the problem. It is different than the degree of a monomial. With a monomial, we just counted up how many variables there were. Like here there's 1 variable, here there's 5, here there's 9, here there's 6. We counted up the number of variables, but we don't do the same with the degree of a polynomial. The degree of a polynomial is equal to the greatest or highest degree of its terms. Think of it as a label. Instead of counting up all the variables in a polynomial, because some polynomials go very, very long, it'd be very tedious to count up, we just look for what's the biggest degree in this polynomial, and that'll be the degree of the whole polynomial. So let's find some degrees. What's the degree of this first term? Well, we know that 7 has no variables in it, so its degree is 0. What about x squared? Or I should say negative x squared. It's degree 2, because there are 2 x's. 3x cubed has degree 3, since there are 3 x's being multiplied together. And 3x just has the one lonely x. Each of these are the degrees of the monomials. But the biggest one is this, right here. The biggest monomial has degree 3 in the polynomial. So we say the polynomial has degree 3. It matches whatever the highest degree is inside of it. So what if we had a problem that looks like this instead? What if we had a polynomial that was nuts? 2x to the 7y squared minus 7x to the 6th y to the 6th plus 2z to the 10th. Well, we just have to figure out what the degrees are for each piece of this polynomial. We've got 7x's and 2y's, so that's 9. 6x's and 6y's, so that's 12. And 10z's, so that's 10. 12 is the highest of these, so we would say this is a polynomial of degree 12, since 12 is the highest of them. All right, y'all, we're almost done with definitions. We've got 2 more to go. We are not going to be talking about closed. We're not going to give a definition for this yet. However, we are going to be talking about standard form and the leading coefficients. Now, having these polynomials is nice, but imagine if we had a really big polynomial stretching on for the entire page. It would be very hard to look at every single monomial inside, find the degree of them, and then pick out which one is the biggest. It'd be a lot of work for us. Instead, we'd like to rearrange our polynomials before we write them down so that it'd be easy for anybody in the future to determine what the degree is. We call this order standard form. And a polynomial in standard form is as follows. A polynomial is in standard form when the degrees of its monomials decrease from left to right. And we primarily only talk about this when we're dealing with polynomials with just one variable in them. That's where we would use standard form. So, let's take a look at this. Let's say I have the following polynomial. Let's say I have 2 plus x cubed minus 6x squared minus x. And I want to put this in standard form. Well, the highest degree must go first. X cubed has degree 3. So we write this down with x cubed going first. The next highest degree is negative 6x squared, because it's got 2 x's in it. Then negative x, since there's one x, and we would add 2. This is this green equation rearranged in standard form. Let's do just one more, and this one's going to illuminate something a little interesting. What if I had something like x minus x squared, well, let's make it 3x squared actually, plus 6. Now, I want to rearrange this in standard form. So what would go in front? Well, we know this negative 3x squared is the biggest, or has the highest degree, so it would move to the front. This minus sign is attached to the 3x squared. This is really saying x plus negative 3x squared, if you were just talking about it in terms of addition. So we would move the minus sign along with whatever it's attached to. It would go negative 3x squared in the front. Then we would have our positive x, so we write it as plus x. Then we have our positive 6, so we write it as plus 6. That is standard form. There's one last thing I want us to take a look at, and that's a leading coefficient. Now, a coefficient is a number that comes before a variable. For instance, in this term, the coefficient would be negative 6 for the negative 6x squared, because negative 6 is being multiplied to x squared. We define the leading coefficient as the coefficient, or number, multiplying our highest degree term. Oops. It's the number multiplying our highest degree term. In standard form, this is actually pretty easy to figure out because your highest degree term in standard form is going to be first. It's always first. So the leading coefficient is just the number that comes before your first term if it's in standard form. We have a leading coefficient of negative 3. All right, y'all, let's do some quick practice before we wrap up the lesson. We've got a couple more things to talk about here, but I want you to turn to page 208. Let's take a look at problem number 9. We want to do the following, and I want you to do this part on your own. Actually, let's do number 9 and number 12. This would be very enriching. I want you to write the polynomial in standard form. Then, after you write it in standard form, identify what degree the polynomial is and what the leading coefficient is. Then, classify the polynomial by the number of terms, meaning is it a monomial, a binomial, a trinomial? Classify it by the number of terms. Pause the video here, try this out for yourself, and we're going to come back in a moment to reveal the answers. Did you get these? So, for number 9, we would rewrite it with the 3x squared first, then the x, and then the 5. Because 3x squared is the highest degree, it's degree 2, because there are 2 x's in that term. The leading coefficient is 3, and it's a trinomial. For number 12, there's one thing that throws a little bit of a monkey wrench into the situation. Yes, we would write it with f to the 4th plus f squared minus 2f. The highest degree term is f to the 4th, that's degree 4, so the polynomial is degree 4. But we don't have a number in front of our f. Remember that when you don't have a number in front of a variable, it's being multiplied by 1 secretly. So we would have a leading coefficient of 1. And this one is also a trinomial. Very nice. We're now going to shift gears just a little bit, and we're going to talk about how to add and subtract polynomials. So if we go down, all the way down to problems number problem numbers, I should say, 15 and 16. As we look at these problems, these are two polynomials being added together. You can see that one of them is in parentheses here, the other one's in parentheses here. And we want to add them together. Do you remember how we added big numbers back in grade school? Well, this is still grade school, but back in like early grade school, like if we had 273 plus 952, instead of adding them side to side, we would usually stack them up so that the digits were in line with each other. For instance, the units digits are here, the tens digits are here, the hundreds digits are here, and then we would add from right to left. 3 plus 2 is 5, 7 plus 5 is 12, so we carry the 1. 2 plus 9 plus that carried 1 is 12. It turns out that for polynomials, when we're adding polynomials, we want to do the same thing. We want to stack our polynomials with each like term on top of each other. Additionally, we like to add when they're in standard form so that we can guarantee each term matches up. So we would write this out like this. X squared plus 3x plus 5 over here, plus we would have our negative x squared plus 6x minus 4. Since we are adding or combining these terms, we combine them vertically. What is 5 plus negative 4? It's the same as 5 minus 4, right? 5 minus 4 is 1. It's positive 1. What is 3x plus positive 6x? That's 9x. And what's x squared plus negative x squared? Now we've got a little bit of a situation here. X squared plus negative x squared is the same as just x squared minus x squared. That's 0. So they cancel out. Our answer is 9x plus 1. Now that's all fun games, but I want to see what happens with a problem like 16. In number 16, our terms are not in standard form. So, your first step should be to put them in standard form. In the first term, the 3t to the cubed has the highest degree, it's degree 3. Then t squared has 2. Then negative 3 is 0. Over here, we have negative 2t cubed is the highest degree. 2t squared is the next highest. And 7t is the last highest. So, when we put them in a stack with each other, we would get 3t cubed plus t squared. But notice how this one doesn't have a t term. It's just t squared and then the ones. I'm going to leave a blank spot where our t term would go and put minus 3 at the end. On the other polynomial, we have negative 2t cubed, we have plus 2t squared, and we do have a t term, but we don't have a units term, like plus 2 or plus 3. So we leave that blank. We basically have these two blank zones here, here and here. This is important, and it's very important that we stack them with this in mind, because if we want to add by stacking, you can only combine things that look the exact same. T squareds can only combine with t squareds. I can't combine a negative 3 and a 7t. So that's why we have these blank spots, to show us that we're just going to move them down. 3t cubed plus negative 2t cubed leaves us just 1t cubed. T squared plus 2t squared is 3t squared. 7t doesn't get added with anything in the first one, so we just write it as plus 7t. And negative 3 doesn't get added with anything in the second, so we write minus 3. That is our answer. One more problem, and then we will be done. Let's say we had a problem like problem number 17, where we're asked to find the difference. In other words, subtract these two. Now, we would stack them up just like before. Thankfully, these are in standard form. We would have g minus 4 minus 3g minus 6. If you wanted to, you could just do negative 4 minus negative 6, g minus 3g, but that's a lot of negatives to deal with. Instead, what I always recommend doing is this, and this will help us out in the long run too. Instead of having a subtraction problem, let's turn it into an addition problem. You see how we have minus everything in parentheses here? We can actually distribute this negative sign into the parentheses, and we'd be left with an addition problem. G minus 4 plus whatever the negative gets distributed out to be. Well, negative distributed to a 3g is negative 3g, and a negative distributed to a negative 6 is plus 6. You can solve using the method that you want. If you want to solve the first one, be my guest, but it'll be a little trickier in the long run. By turning it into an addition problem, all we have to do is g plus negative 3g, that's negative 2g. Negative 4 plus 6 is positive 2. If we did it over here, g minus 3g is negative 2g, and negative 4 minus negative 6 is the same as negative 4 plus 6, just plus 2. You get the same answer, but this way it deals with less negatives. I would always recommend turning it into an addition problem. All right, everybody, that's a wrap for today's notes. Thank you so much for listening, and I hope you have a fantastic rest of your day.